Okay, the first few minutes of this presentation are going to cover literally everything that you need to solve practical problems that I'll be giving you, for instance, the one in the take-home exam related to fluorescence spectroscopy. So this will be kept incredibly simple. I'm not going to worry at all at the moment whether you understand the bigger picture, whether I've conveyed an understanding of the bigger picture. After I go through this brief practical synopsis of what you need to know to solve the problem, I will explain a lot of this in detail, but the first few minutes are sort of just the facts, Jack, relative to the problem set. So to keep it as simple as possible, when you have a excited state population that's in the process of undergoing fluorescence, a number of different properties sort of compete, as it were, for excitation, for decay, and removal of the excitation energy. One of those processes is fluorescence. That's the one that we're going to observe. That's the one, in some sense, we care about the most. The fluorescence emission is described by a certain rate constant, which we're going to call gamma. But competing with fluorescence emissions are other processes which are described by other rate constants. These are all first order, these are unimolecular processes. They're first order rate constants. They're going to be describing basically single exponential decay kinetics. The total rate of decay of the excited state population is going to be given simply by the sum of all these first order rate constants. So that's just shown here. So this is the first relevant equation. I'm not sure you actually even need to use this one directly, but it is closely related to the two that you will need to know. So the total rate of decay of the excited state population is given by the sum of the fluorescence decay rate, the thermal decay rate, the collisional quenching rate, the fret rate. So the sum of all these rates describes the unimolecular first order single exponential decay of the excited state population down to the ground state. Now, what we care about in the experiment, is what fraction of the excited state population is admitted as fluorescence. The fluorescence process, as I'll discuss, an actual fluorescence experiment involves sort of more complicated dynamics. But we can ignore all of those dynamics and focus simply on the relative amount of energy that's given out at any moment in time as fluorescence compared to the relative amount of energy that is given out or to other kinds of decay processes, right? And so if at any sort of moment while we're observing a fluorescent population, the relative rate of fluorescence decay is, let's say 80% of the total amount of decay, because that same kinetic partitioning will apply at any point in time in any measurement that we're making. The relative yield of fluorescence, which we call the quantum yield, is just going to be given by that kinetic partition ratio. So the quantum yield, which is the fraction of absorbed photons emitted as fluorescent photons, right? That's, the quantum yield is simply the fraction of emitted photons emitted as fluorescent photons, right? That's the definition of quantum yield, right? And so, as I'm going to tell you in a moment, that's essentially what we're measuring in intensity experiments. But the quantum yield, and again, the dynamics, the population dynamics of this actual experiment are more complicated, but it doesn't matter. The net thing that we observe in intensity measurements, what we observe is something proportional to quantum yield. Quantum yield is the fraction of absorbed photons emitted as fluorescent photons. We can ignore all the population dynamics and simply calculate the quantum yield as the rate of fluorescent emission compared to the total rate of decay. Again, if at any moment in time, let's say 50% of the decay at some instant in time is fluorescence and 50% of the decay is everything else, then we have a partitioning ratio, basically, 1/2. The kinetic partitioning will be 1/2. 1/2 emitted as fluorescence, the other half emitted as everything else. That kinetic partition applies at any point in time, and so the quantum yield we will observe, no matter how we do the experiment, will be simply given by that kinetic partitioning ratio. Now, to solve simple real-world problems, you will need to know basically this equation and just one other equation, which is the quantum yield is equal to the fluorescent decay rate constant, the fluorescent emissions rate constant times lifetime. So what is lifetime? This will be explained more carefully later in the presentation, but to give you what you need to know to solve the problem, you really don't need to know anything more than the fact that lifetime is the reciprocal of this total rate constant, right? So basically, the denominator in the quantum yield equation is equal to the total rate of decay of the population. The total rate of decay is going to be the reciprocal of the lifetime, right? These are monoexponential processes. The lifetime is the amount of time it takes to decay to 1 over e of the starting population. For simple monoexponential, the rate constant is equal to 1 over the time constant. This time constant is called the fluorescent lifetime. The quantum mechanical equation, the quantum yield equation is the fluorescence emission rate over the over the total decay rate, meaning in the end this is the emission rate times the reciprocal of the decay rate. The reciprocal of the decay rate is the lifetime. Why do we care about that in terms of practical problem solving? Because you can measure lifetimes. The rest of the presentation will explain to you in detail how this is done, but you don't actually need to know that to solve the problem. To solve the problems on the test, all you need to know is this expression for quantum yield and this relationship between the quantum yield and the lifetime. You also need to know that quantum yield is measured effectively in a steady state or continuous illumination steady state intensity experiments, right? And so very quickly, again, this will be explained in more detail later, but to give you the minimum bare bones that you need to know, but to completely and effectively solve the problem, right? In most experiments, what we'll do is we will continually excite some volume of fluorophores. Under those continuous excitation conditions, we will have a steady state process where, sort of one at a time with some probability fluorophores are being excited, and then they're, according to the intrinsic kinetics controlling the decay process, they will decay. When we do a continuous illumination experiment, we basically have a steady state where there's a balance between ongoing excitation and ongoing decay and fluorescent emission. And so we'll basically have over the time of continuous illumination, we will rapidly achieve a steady state where there is a constant illumination, constant rate of excitation, constant rate of fluorescence emission. In the simplest form of intensity experiments, we measure the fluorescent emission in that continuous illumination steady state mode. But it turns out the intensity we get there is linearly proportional to quantum yield, right? And so really to solve the practical problem, that's all you need to know. The intensity we measure in a continuous illumination experiment under steady state conditions, that intensity is proportional to the quantum yield. Why and how is explained in more detail later in the presentation, but for just the facts jack presentation, that's all we need to care about. So quantum yield, which is equal to the product of the fluorescence emission rate times the fluorescent lifetime, and defined as the fraction of absorbed photons re-emitted as fluorescence, it can be measured directly, but it requires very careful calibration of linearity and response of response in solid angle captured by photon detectors. You don't need to worry about this. The bottom line is you can measure quantum yield directly. Usually we don't. What we generally measure, and what's assumed that you are measuring in the problems that I've given you, is relative quantum yield. Relative quantum yield and changes in quantum yield are measured by comparing fluorescence emission intensity, which is linearly proportional to quantum yield when measurements are made in the simple conditions when we make measurements. I'll go through these caveats very quickly later on. For the moment, they don't even matter. They don't matter. The bottom line is fluorescence emission measurements, as they're typically done, fluorescence intensity measurements, simply give you a quantity proportional to quantum yield. So in an experiment where you're varying, let's say, quenching parameters in non-fluorescent decay parameters, and thereby varying fluorescence decay rate and fluorescence lifetime. In that simple experimental mode, the intensity you measure is going to be proportional to quantum yield. The quantum yield is the product of the fluorescence emission rate, which you can't measure, times the fluorescence lifetime, which you can measure. So to solve practical problems, that's really all you need to know. Now, you need to know one other thing. You need to know what kind of anisotropy, how we measure the what you need to know what basically anisotropy parameter or value we get out of these continuous state measurements. That's the only other thing you need to know to solve the problem. And so quickly step through that. Instantaneous emission intensity and anisotropy can be measured on a nanosecond time scale after pulse femtosecond laser excitation of a fluorophore population. Later on, we'll talk a little bit more about these details and how this works and how it relates to everything else. For now, we're just going to move on to, again, the point. Much more commonly, steady-state emission intensity and anisotropy steady-state emission intensity and anisotropy are measured using continuous illumination of a population. As I just told you, that steady-state emission intensity is linearly proportional to quantum yield. What do we measure in terms of what do we measure as steady-state anisotropy? Well, what we measure is the fluorescence observed during what we measure in terms of steady-state anisotropy. We can figure that out by considering the fact that the fluorescence observed during continuous illumination, it integrates the time-dependent decay and rotational probabilities of the individual molecules in the illuminated population. Okay, and so basically what you're having when we do steady-state experiments, we're integrating all these molecular processes that occur between the emission of individual fluorophores between the excitation of individual fluorophores and the emission of fluorescence. Although that happens sort of molecule by molecule, when we look at a population, we're basically integrating over the behavior of the ensemble of molecules. And when we integrate over the behavior of the ensemble, we are ultimately integrating over the probabilistic behavior of individual molecules, right? And so, again, later I'll explain that in much more detail. But for the moment, what's the point? Well, the point is that when you do that integration, we get a value of anisotropy that depends on fluorescent lifetime and rotational correlation time. So rotational correlation time is basically the probabilistic rate of reorientation of the particles. This is shown in the next slide. So the rotational correlation time, basically anisotropy actually gives you a direct measure of the rotational correlation time. If we do a pulsed femtosecond excitation and look at both we can look at the intensity, the instantaneous fluorescence intensity as the population evolves and decays after that. We can also look at the instantaneous anisotropy, right? So as the particles are rotating, the anisotropy will decline. Basically, as the particles rotationally diffuse, it's a probabilistic process, but as time goes on, more and more of them will have changed their orientation and lost memory of their starting orientation. The math of anisotropy is such that the decay in anisotropy is described by a single exponential. The time constant for the single exponential is something called the rotational correlation time. That's the very, very clever part of anisotropy. That's why that is a clever numerical value. It is related in a very simple way to an important and simple physical property, the rotational correlation time. So the bottom line is we can measure fluorescence lifetime through these kind of pulsed nanosecond excitation experiments. We can measure rotational correlation time. The only thing that matters in terms of the practical problems that we want to solve on the exam is what do we measure as steady-state anisotropy, right? Again, usually we're not doing these pulsed experiments. Usually we're measuring things under steady-state conditions. This is slightly complicated dynamically, but in the end there's a very simple result. The steady-state anisotropy is a simple mathematical function of the photoselection anisotropy. That's the maximum anisotropy you can get when the population is initially excited because of something called photoselection, described briefly in the overview presentations. You can only get a certain maximum value of anisotropy. When you do any excitation, initially you will have that maximum value of anisotropy. That value of anisotropy over the time course of emission will decay as a single exponential with a time constant equal to the rotational correlation time, right? So the steady-state anisotropy will simply be the product of the initial photoselection anisotropy times the reciprocal of the quantity 1 plus the ratio of the fluorescence lifetime to the rotational correlation time. So again, both of these parameters are measurable in pulsed excitation experiments. But typically, what we're going to be measuring are these parameters under the conditions of continuous excitation. The steady-state anisotropy is related by a simple mathematical function to the steady-state anisotropy, which is what you measure under continuous illumination conditions. is a simple mathematical function of the initial maximal possible photoselection anisotropy and the fluorescence lifetime and the fluorescence and the rotational correlation coefficient. We can measure these things directly, but usually instead we're going to be measuring them indirectly by using anisotropy. And fluorescence lifetime, as I showed you earlier, is related to quantum yield, and quantum yield is linearly proportional to the emission intensity in a continuous illumination experiment. And really, that's all you need to know to solve the problems on the test. You don't need to know anything beyond that. Now next, I'm going to sort of explain how all this stuff fits together, go through the math in some detail, hopefully provide an explanation that complements that in Lacowitz. I think Lacowitz explains this stuff reasonably well. Could be true the explanation is starting at a point of understanding a bit ahead of where some of you are. And so next I will try now to fill in the gaps and provide an explanation that goes continuously from where you are to a pretty complete understanding of this. But you don't actually need to know any of that to solve the problems. What you need to know to solve the problems is basically this equation in the equations I showed you earlier at the outset of the presentation describing fluorescence quantum yield and the relationship between quantum yield and lifetime. Okay, so let's back up now and go through all of this again in greater detail. Again, I don't think you need this stuff to solve the problems. What you need to solve the problems is what I just told you, plus a very healthy dose of the stuff we covered in the first half of the semester. But it could be useful for your, hopefully it is useful for your education and maybe useful to help you wrap your mind around the problems to go through it all more carefully. And so that's what we're going to do now. So fluorescence is tremendously useful in many areas of science and technology, including cell biology, molecular biology, biochemistry, biophysics. It is perhaps probably the most widely used sort of biophysical method across all areas of biomedical research. So it is worthwhile to understand the physical processes involved in fluorescence. The limitations, some of these things are limitations that end up being important for the cell biological applications of fluorescence. Recently there have been actually a Nobel Prize awarded for sort of a clever exploitation of what initially seemed to be peculiar properties of fluorescence that require sort of digging into the physical chemistry of it more deeply than we're going to be able to do. But as sort of a baseline area to understand fluorescence, we want to consider what we can actually observe and how the physical processes affect what we actually observe in the laboratory. And so the purpose of this screencast is to cover that and to thereby empower you to understand and solve related problems. And these are problems that reflect, again, things you would actually measure in the laboratory and things that are quite useful to do to understand the biophysical properties of systems, and then also to understand sort of technically what's going on in many other applications of fluorescence. So the starting point for this, a good starting point for these considerations is, of course, the Jablonski diagram. The Jablonski diagram. The Jablonski diagram schematizes the different molecular quantum states involved and, importantly, the different processes that move fluorophores between the different quantum states. As we discussed before, internal conversion and solvent relaxation tend to put the excited state electron into the ground vibrational state, and the electronic excited state also tends to move everything into the lowest energy electronic excited state. From that state, most fluorescence emission occurs from that state. And so the fluorescence emission will have a certain time-dependent probability, but other processes that remove excitation will also have time-dependent probabilities. And ultimately what we will see in terms of the yield that we get out of an excited state of fluorophore depends on the relative rate of all these kinetic processes. So again, the Jablonski diagram nicely summarizes what processes are involved. It doesn't directly show the kinetics. We're now going to have to dig into the kinetics. And so when we're looking at kinetics, it's going to be a useful point of analysis, and in some cases a useful thing to measure, the rate of decay of the excited state population. And so that's what we're going to look at first. We're going to look at how an excited state fluorophore population decays with time. Okay, and so because all of the, assuming all of the molecules have equivalent physical properties, the total rate of decay of the population will reflect the probability of decay of each individual molecule. So we're in the population. So we're going to look at that somewhat closely. And so in the end, those decay processes, they're first-order kinetic processes. First-order kinetic processes give single exponential behavior. And so, very important point. If we want to look at how fluorescence changes with time. And so the model we're going to use here is something called a pulsed nanosecond excitation. Actually, sorry, that should be femtosecond excitation. After a pulsed femtosecond excitation, an excitation of the population on a time scale much shorter than the fluorescence process, an excitation on the time scale of the absorption process, we will get a population in which some number of fluorophores are excited. Then we can watch the evolution of that population with time. And this is something that we can do experimentally. I'll show some schematized examples of that in a moment. But it also is the most useful way to think more generally about what we're going to observe when we do any kind of fluorescence experiment. And we'll come back to that at the end of this screencast. By the time we've done that, you will be fully empowered to solve a lot of practical problems related to fluorescence, including all of those that are covered on the exam. And the number of equations we need to do that is small. We really only need about 3 or 4 equations to take care of all of that. And those are relatively simple equations mathematically. How they fit together conceptually is maybe a little bit complicated, and since I've been doing this for many years, maybe a bit more complicated than it seemed to me, and the discussions with some of you have helped me understand maybe what some of those complications are in linking the simple math to what we really want to get at, were experimental observables and understanding of the underlying physical processes. Okay, and so what we will see is that if you look at an excited state population, so for the moment, let's just say we have a population of fluorophores that have been excited and that have then decayed down to the ground, to the lowest energy excited electronic state, and the solvent relaxation process has occurred. And so all of this has occurred on a sub-nanosecond timescale. And so now we're looking at the evolution of this excited state population on the nanosecond timescale. During the period we're looking at it, fluorescent decay will compete with collisional quenching, perhaps FRET, and then other forms of non-radiative decay. And so we'll have a kinetic competition between these different forms of decay, and that kinetic competition, there'll be a kinetic competition between fluorescence and these other decay pathways, but all of these decay pathways will contribute to the overall rate of decay. And so the total rate of decay of the population is simply given by the first order rate constants. Right? This is the first order rate constant for the decay of the entire fluorescent population. That rate constant is simply the sum of the rate constants for the individual decay processes. They're all occurring on equal footing in parallel for molecules in the excited electronic state. So to get the total rate of first order rate of decay, we simply sum the rate of the fluorescence emission, the rate of the other kinds of non-radiative thermal quenching, the rate of collisional quenching, if there's such a thing going on, and the rate of fret, if there's fret going on. So again, this is quite simple. The total, this is a first order kinetic process. We have a single population. There are different ways for it to decay, but the total decay rate is simply the sum of all those rates. And because this is a first order process, then what we will see is the entire population will decay with single exponential kinetics. So the fluorescence at a given point in time will be given by the initial fluorescence whenever we start doing the observation. We'll come back to that in a moment, times E to the negative K total, right? This is K total, times T, right? So this is a first order exponential decay, simple first order exponential decay. We get that because this is a first order kinetic process, right? We're looking at one molecule. There's a given probability per unit time for each one of these processes happening. We sum them up and we get the total first order probability per unit time of losing the excitation. And so we will see a mono-exponential decay characterized by this rate constant K total. K total is simply the sum of the individual decay, the rates for the individual decay pathways, as shown down here. Now, an important, sort of reference point that presumably you've heard about before is something called the lifetime. The lifetime is the time it takes a single exponential, well, the lifetime of a process is defined as the point at which a population goes down to 1 over E of its initial value. So in this case, the fluorescence lifetime will be given by the time it takes the excited state population to decay to 1 over E of its initial value, right? So however many fluorophores are in the excited state, the lifetime will be the time it takes until there is only 1 over E of that number that is left in the excited state, right? And so we can just look at that simple, we can look at, that the mathematics describing that. If we describe that fluorescence lifetime by a variable tau f, right, when the observation time t is equal to tau f, this quantity, right, if t is equal to tau f, we will have e to the negative tau f over tau f, or e to the negative 1, right? And so this simple exponential form is an easy way for us to see what the fluorescence lifetime is, right? Again, fluorescence lifetime is defined, the lifetime of a kinetic process is defined as the time it takes it to get to 1 over E of its initial value, right? In this equation, if we plug in, if we let T equal tau f, fluorescence lifetime, we get E to the negative 1, which is 1 over E, right? By comparing the kinetic equation by comparing this exponential equation that describes the total rate of decay to this exponential form expressed in terms of the fluorescence lifetime, we can see that the decay rate, K total, is equal to 1 over the lifetime, right? And so we'll come back to this in a moment. But this is for a single exponential process. This is always going to be true. Again, it's just looking at the relationship between the exponential decay process expressed in terms of first order rate constant and the exponential decay process expressed in terms of lifetime, the time it gets to 1 over E of the initial value. Just by comparing these two equations, you can see that the kinetic rate constant is equal to 1 over the lifetime, right? So the total rate of decay, the first order kinetic rate constant for the decay of the excited state population is simply the sum over the different molecular processes that cause decay. That sum is going to give you the first order rate constant. That first order rate constant is the reciprocal of the lifetime. So that's again, simple math, maybe a little bit more complicated in terms of understanding physically what's going on. And so now what we want to do is, ultimately what we want to do is understand how now the observed fluorescence is influenced by the competition between these different decay processes. But before we do that, let's just look a little bit more closely at this decay process. I think that will help. You don't actually need to use the information in the next slide to solve the practical problems that I've given you, but I think this information might help consolidate your understanding. So let's go on to that. All right, so what we're going to do now is consider what happens experimentally, and we're going to sort of initially do that by, in general, what happens in an experiment. You have a population, you have a sample with fluorescent, oops, that a little bit too fast. In general, what we'll have is we'll have a population with fluorescent molecules, I'm sorry, with a population of fluorophores in a cuvette of some kind. We will excite, we will shine light on that cuvette. This will be excitation light. The light may be polarized. We'll come back to that later. The light will be absorbed with some efficiency described by the molar extinction coefficient for the fluorophore. That will put some fraction of the fluorophores into the excited electronic state. Once they're in the excited electronic state, they will decay according to the processes we looked at in the previous slide, with all of them contributing in parallel to the net observed decay and decay rate. And we will then observe the fluorescence. We'll do that at a right angle to the excitatory light. We do it at a right angle because although fluorescence is extremely sensitive, the fraction of light that gets emitted at fluorescence is quite small compared to the input light. And if we try to observe the fluorescence in the same direction of the input light, it's not impossible, but it's a much more complicated thing to do. So in practice, because the magnitude of the fluorescence is generally much smaller than that of the input light, we observe the fluorescence at a 90-degree angle. So this sort of experimental setup is schematized down here. This diagram actually shows a polarized fluorescence measurement. We won't worry about that now, but we'll come back to it later. So now up here is supposed to schematize, these are both figures taken from Lacowitz. Up here is supposed to schematize what's going on in terms of the fluorophores in this population in the cuvette. And so let's think about that. So actually, experimentally, it is possible to excite a fluorophore population on a femtosecond time scale. And so this is the Cropper time scale. This is a typo. Sorry about that. So they're lasers that can be gated so that you get a pulse of light going through the sample that lasts some number of femtoseconds. This pulse will last, many, anywhere from 10 to 100 wavelengths of the excitatory light, but the time scale of the time it takes one wave to sort of pass a point is in the low femtosecond range, and so a train of 10 to 100 light waves still can be sent through the sample, on a femtosecond time scale. So basically, on a time scale that's short compared to the fluorescence emission process, we can excite the population. This pulse will not excite all of the population, but with some probability, each molecule in the population will absorb a photon, and then we will get some fraction of the population in the excited state, as shown by the Jablonski diagram. By the time we hit 1 nanosecond after the time of the excitation, essentially all of the molecules in the population will have decayed to the lowest energy electronic excited state in the lowest energy vibrational quantum. The vast majority will be in the lowest energy vibrational quantum state. So at that point, we can observe what happens, right? So we'll have some number of fluorophores in the excited state in our cuvette. We will have turned off the light by that time, and then we can just look at how that population decays. So the decay of that population will be described as the overall rate of de-excitation. So it's a simple exponential function where the rate constant is simply the sum of the single the overall rate of decay of the population will be given by the sum of the first order rate constants, right? This will be a first order rate constant for the population decay. It is simply the sum of the first order rate constants for each of the processes that is removing the excitation from the population. And again, we will call that K total. And so the fluorescence intensity as a function of time will just be whatever the fluorescence intensity is at time 0, right? At time 0, a certain fraction of the population will be giving out its excitation energy as fluorescence. We'll come back to this in the next slide. But as the total population in the excited state decays, the amount of fluorescent emission will decay. And so we'll see the fluorescent emission intensity decline with time. The rate of that decay will be given by K total, the sum over the individual first order rate constants for all the decay processes. K total is equal to 1 over tau f, where tau f is the fluorescence lifetime. When you hit a time of tau f, the population will have decayed to 1 over e of its initial value. The fluorescence level will be 1 over e of its initial value. So depending on the total rate constant for decay, we can have a shorter lifetime, we can have a longer lifetime. And so faster decay, shorter lifetime, slower decay, longer lifetime. By looking at the time point at which the population hits 1 over e, we will know the lifetime. From that, we can calculate as the reciprocal the total decay rate. So that's I think the pulsed nanosecond, the pulsed femtosecond excitation experiment is hopefully, and again, this can be done in a laboratory. We need equipment that costs about $100,000, but this stuff is around. This is a relatively simple experiment to do. It enables us to just directly observe the decay of the fluorescent population. Okay. Now, of course, during this fluorescence emission period, a number of things are happening. So during the same period where the fluorescent decay is happening and the other pathways that remove excitation or proceeding, during that same nanosecond time period, the molecule will be rotationally reorienting. And we're going to come back to that later. There's basically simultaneous decay from the excited state. Decay from the excited state is proceeding simultaneously with rotational reorientation. Now, in terms of individual molecules, those are both stochastic or probabilistic processes, right? When we look at the entire population, of course, we'll see the population decay according to a particular rate constant. But the rate constant we see in the population will actually be the same as probabilistic rate processes going on in each individual molecule, right? And so we're going to observe this overall rate of fluorescence decay in the population. That process will reflect that ensemble process, right? That process in the ensemble of molecules that went into the excited state will reflect probabilistic kinetic processes going on in each individual molecule. So that's an important point. So every individual molecule in the excited population will decay from the excited state independently from the others with some time-dependent probability that will be equal to the sum of the probabilities for every mechanism, right? So the probability of decay per unit time for a given fluorophore will be the sum of the probability of decay per unit time for each of the individual decay processes. The total probability of decay per unit time for a given fluorophore will be equal to the decay rate of an ensemble after the pulsed excitation, right? So this is a first-order kinetic process. The decay probability per unit time for each individual fluorophore is going to match the decay rate of the population. So these rate constants describe both the time-dependent probabilities of the individual decay processes. There's some will be the time-dependent probability for decay being any pathway. That sum will match the first-order rate constant for the decay of the population as observed here. So you don't necessarily need to do this math yourself. You probably don't need to do this math yourself, or even necessarily think about it to solve the practical problems that I've given you relative to fluorescence spectroscopy. But perhaps it's useful to understand how all this fits together to get a better conceptual grip on what's going on and understand a bit more deeply what we're trying to get at in these problems. Okay. So one final point. Although you can do these kinds of pulsed experiments and then actually watch on a nanosecond. So in the pulsed experiment, the light is turned off for a short period of time, and you watch over a nanosecond time scale the decay of the population. Usually in an experiment, what we're doing is actually continuously exciting the population. And so as we do that, there'll be a certain probability per unit time for an absorption to occur. And then as each molecule absorbs light, it will undergo internal conversion in solvent relaxation. And then that individual molecule will have a certain probability of decay per unit time. And so what will happen when we continuously illuminate the sample, we'll effectively achieve a steady state where there's a certain rate of excitation of the molecules in the population, and the rate of their decay will eventually match the rate of excitation, will quickly match the rate of excitation. And so we'll see that sort of steady state process when we have continuous excitation of individual molecules and continuous decay of individual molecules. Now that is maybe slightly complicated physically, but we'll see if we look at the math from a certain simple and clever angle, we can capture those steady state effects in a very, very simple way. And we're about to look at sort of what the steady state quantum yield or intensity will be. But ultimately, the continuous illumination is integrating over the behavior of all of the individual molecules in the population. And so that's going to be an important point when we think about what kind of anisotropy we're going to get out of a population under conditions of continuous excitation. So we're going to come back to that in a couple minutes, but in the meantime, we're going to look at what kind of intensity we get during continuous excitation of a population. All right. So this is just coming back to where we were before. It's just reminding you, I will remind you that the total rate of decay from the excited state population is given by the sum of the individual decay rates. The reciprocal of that sum decay rate will give the fluorescence lifetime. That fluorescence lifetime, again, reflects a mono-exponential decay of a population in the excited state. So now, for any fluorophore in the excited state, there will be a given probability per unit time of fluorescence decay, but also a given probability per unit time of losing that the excitation energy through non-fluorescent pathways. What we want to know now is, what is the amount of fluorescence? What is the intensity of fluorescence we're going to see under continuous excitation conditions in an actual experiment, and how that relates to the molecular and physical properties. Okay. And so the way we're going to do that is look at something. We're actually going to look at fluorescence intensity. We're going to observe fluorescence intensity experimentally. But fluorescence intensity is going to be simply related to something called quantum yield. So the quantum yield Q is defined as the fraction of absorbed photons emitted as fluorescent photons. And so in some, under continuous excitation conditions, this is actually quite a complicated sort of physical process involving steady state equilibrium between excitation and decay. But there's a very simple way to get at the mathematical heart of this. We can just consider the fact that at any moment in time, there's a kinetic partitioning between fluorescence and all of the other decay processes. The fraction of the excited state population that will produce fluorescence will match the relative rate of the fluorescence process compared to all of the kinetic processes that remove excitation. So at any moment in time, the fraction of excited state fluorophores that emit fluorescence compared to the total fraction, the fraction of fluorophores emitting fluorescence compared to the total number decaying at any moment in time is simply going to be given by the ratio of the rates. So the rate of fluorescent emission divided by the total rate of decay is going to give us the quantum yield. And so although we're going to quantify quantum yield typically we will quantify this under continuous illumination conditions. Well, there'll be a complicated steady state process going on in the background, but we don't have to deal with all of that math and all that complexity. We can focus on the simple point that if the partitioning ratio, whatever the partitioning ratio is of the excited state between fluorescence and other decay processes, whatever that partitioning ratio is at any moment in time will be the overall partitioning ratio we will see integrated through time. As long as the partitioning ratio is the same at all times, the instantaneous partitioning ratio will give what we see when we integrate over all times. So that's an important point. In the end, you could ignore all of that, because the bottom line is the quantum yield, which is related to the intensity that we observe. We'll talk about that in a moment. The quantum yield is described by this very simple equation, the fluorescence decay rate over the total decay rate for decay via all pathways. So really, to solve practical problems, all you need is this very simple kinetic partitioning equation. Again, it reflects the fact that if at any instant in time, let's say we have 1/4 of the fluorescence being emitted, let's say at any instant in time, 1/4 of the molecules in the excited state emit photons and fluoresce, and 3/4 of the molecules in the excited state are relaxed via other pathways, right? If at any moment 1/4 of the decay from the excited state is occurring via fluorescence and 3/4 is decaying via other pathways, well, again, these are first-order kinetic rate constants, right? These are unimolecular first-order kinetic rate constants. Whatever occurs in the population at one moment in time is going to be what happens in the population at every moment in time. So if 1/4 of the fluorescence is being emitted, if 1/4 of the de-excitation is occurring at fluorescence at any moment in time, 1/4 of the total de-excitation will be emitted as fluorescence integrated over all time. So we don't have to explicitly do the integration. We can just look at the kinetic partitioning ratio, and that kinetic partitioning ratio will give us the quantum yield under any circumstances, including complicated steady-state continuous illumination circumstances. So we can take what is, a rather complicated ensemble situation, but reduce it to very, very simple math, giving the quantum yield simply as a function of the kinetic partitioning, the ratio between the rate constant for fluorescent emission divided by the rate constants, the sum of the rate constants for all possible decay plus pathways. Now, if you look at the equations here, up here we show that the rate constant for the total rate constant for decay of excitation is equal to 1 over the fluorescence lifetime, right? And so that means the total rate constant for decay of the electronic excitation is 1 over the fluorescence lifetime. That means that the fluorescence lifetime is equal to the reciprocal of the total decay rate, right? So over here what we have is the fluorescence emission rate constant times the reciprocal of the total decay rate. So we can replace that with the lifetime, and we get this exceedingly simple relationship. The quantum yield is equal to the fluorescence decay rate times the fluorescence lifetime, right? So now what will happen under experimental situations, the lifetime will change. Like say we change we put in more of or we decrease the spatial proximity of some species that undergoes fret to a fluorophore. Say we put in a collisional quencher. Say we change temperature, which will increase the rate of thermally induced decay from the electronic excited state. So in given experimental situations, what will happen is that we'll be changing and in some cases manipulating these non-radiative decay rates. If we do an experiment with a collisional quencher, that's what we're going to do. We're going to change the rate of the collisional quenching, decay by collisional quenching. In a fret experiment, we will be changing the rate of decay by fret. By changing the temperature, we can change the rate of thermal de-excitation. So during experiments, we will manipulate these non-radiative decay rates, but this fluorescent decay rate, the fluorescent emission rate constant is pretty much independent of anything that we can do in the course of experiment. The fluorescent decay rate, the fluorescent emission rate, is essentially an inherent property of the fluorophore, right, determined by quantum mechanics that set what the molecular orbitals look like, and quantum mechanics will also effectively set the rate of spontaneous decay. Spontaneous emission of fluorophores. So all those quantum mechanical properties that are intrinsic to the molecule will set the fluorescence emission rate. So basically the fluorescence emission rate in experiment will not change. What will change is the rate of the non-radiative decay processes, which means that the fluorescence lifetime will change. So what we'll be doing is, we'll be changing these non-radiative contributors to lifetime, right? All of these things. In an experiment, typically what we will be doing is we will be, again, these terms will be changing in the course of the experiment. Because these non-radiative rate constants change, the lifetime will change, but the fluorescence emission rate constant will generally not change. It turns out that we can measure quantum yield, in some cases directly, and as we'll talk about in a moment, usually indirectly. And so we can measure quantum yield. We can measure fluorescence lifetime using an experiment of the kind I showed you in the last slide. We cannot directly measure the fluorescence emission rate. But if we can measure quantum yield and we can measure fluorescence lifetime, which we can get the fluorescence emission rate indirectly via measurements of quantum yield in lifetime is in what we do. But to summarize the most important point, in a given experiment, well, the two most important points. So first of all, even though we do actual fluorescence experiments under complicated sort of steady-state continuous illumination conditions, we can understand the key process. We can understand how quantum yield behaves simply by looking at the kinetic partitioning, because since these are all first-order rate constants, they will be the partitioning will be identical at any point in time. And so by looking at the partitioning instantaneously, we can know how the energy has been distributed, even integrated over time or under some complicated steady-state condition. So the kinetic partitioning gives us it gives us a rigorous value for the quantum yield that we can get simply by considering the relative kinetic rate constants without worrying about all those complicated population phenomena. So that's important point one. Important point two is quantum yield. It will be directly proportional to lifetime, right? In a given experiment, experimentally, we will not be manipulating fluorescence emission rate experimentally. That's, again, sort of set by molecular quantum mechanics. What we will be manipulating experimentally is the rate of these different non-radiative decay processes. So as we manipulate them, if we put in sort of more quenching species or increase the rate of non-radiative decay, as this rate increases, right, lifetime is reciprocally proportional to rate. If we increase the total rate of decay, lifetime will go down. If lifetime goes down, quantum yield will go down. So what we will be doing in individual experiments is sort of manipulating non-radiative decay rates. Those will change lifetime. Quantum yield will move around proportional to the lifetime, but basically lifetime is reciprocally related to decay rate. As we do things that increase decay rate, lifetime will go down, quantum yield will go down. And so that's the essential content here. I guess tying together, understanding how all of this stuff fits together is a bit complex, but in the end, these two simple equations are all you're going to need to solve practical problems, looking at what we actually observe in the laboratory as we manipulate things to change non-radiative decay rate compared to fluorescent excitation rate. So the next slide is supposed to really sort of summarize those points. And so let's just go through them one by one. We've gone back here now to considering the experimental setup. And so what we're doing now is we're considering how the considerations in the previous two slides are related to what we can actually observe in an experiment. So this first point reiterates what we've already just been through. Quantum yield, which is equal to the fluorescent emission rate times the total fluorescence lifetime. Quantum yield, which is the fraction of absorbed photons re-emitted as fluorescence, can be measured directly, experimentally, but it requires very careful calibration of linearity of response and solid angle captured by photon detectors. The details here are not particularly important, but the idea is if we carefully look at how many photons are absorbed by a sample, and then we carefully look at how many total photons are emitted by a sample, doing that we can measure quantum yield. And that can be done, but that's a rather tricky and difficult measurement, but it can be done, and that's if you look online for fluorophores people typically use, you can find quantum yield values. It's done by doing careful experiments of that kind. More generally, what we'll be doing, in what I'm asking you to do in the problems I've assigned to you, the experiments I'm describing, in the experiments I've asked you to analyze, what happens is relative quantum yield and changes in quantum yield are measured by comparing fluorescence emission intensity. Now, fluorescence emission intensity is linearly proportional to quantum yield when measurements are made in a single instrument with a constant optical configuration and detectors with linear response over a relatively small intensity range. So the details here, this is a rather complete description of the requirements. For your purposes, these details are not important, but I did want to specify them for the sake of rigor. The important point is that fluorescence intensity measurements in a given instrument on a given sample are linearly proportional to quantum yield. So the point is that what we're going to be changing in the experiment are the non-radiative decay rates. If we increase non-radiative decay rate, relatively less excitation will be emitted as fluorescence, right? There'll be more non-radiative decay, more quenching from various pathways. If we increase the rate of the non-radiative processes compared to the fluorescence rate, emission rate, which is constant, the net amount of energy we get out as fluorescence will go down, right? That is, the amount it goes down will be directly proportional to the quantum yield, right? So again, that kinetic partitioning calculation, the simple kinetic partitioning calculation in the preceding slide tells us everything we need to know. The emission intensity here will scale linearly with quantum yield, more or less in a fluorescence experiment. We're measuring, well, the intensity in a fluorescence experiment to a good approximation is going to reflect the quantum yield. To get an absolute quantum yield value, we have to do the experiment very compulsively, but in any old fluorimeter under any old circumstance, when we measure intensity and then we change, quenching or whatever, we're going to be measuring the relative quantum yield. So our measurable via intensity measurements quantify relative quantum yield. When intensity doubles, quantum yield will be doubling. When intensity goes down by a factor of 2, quantum yield is cut in half. And so via simple continuous illumination intensity experiments, we capture quantum yield as described by the kinetic partitioning equation given in the last slide. So as I showed you 2 slides ago, instantaneous emission intensity and anisotropy can be measured on a nanosecond time scale after pulsed femtosecond laser excitation of a fluorophore population. So we've already explained that. But much more commonly, steady-state emission intensity and anisotropy are measuring using continuous illumination of a population. Again, under these circumstances, we're just going to turn the light on, leave the light on. While the light is on, these individual molecules will be behaving, probabilistically, stochastically. They will be, absorbing light with a certain probability. They will be emitting it with the probabilistic rate constants we've talked about in the previous slide. Under continuous excitation conditions, you will get a steady state where there is a equal rate of excitation and emission at any point in time during the time course of the steady state or continuous illumination measurement. So mathematically, physically, that is a bit complicated. In terms of looking at intensity or quantum yield, however, we can ignore all of that complication because, again, the kinetic partitioning is just going to give us the relevant amount of excitation emitted as fluorescence compared to non-radiative decay. So in calculations of quantum yield, we can just ignore all of that complexity. However, when we look at anisotropy, we're going to have to think, when we want to understand what happens with steady-state anisotropy, we're going to have to think about that complexity, which is the only other thing that we need to do to enable you to solve all the relevant problems. So the fluorescence observed during a continuous illumination experiment integrates the time-dependent decay and rotational probabilities of the individual molecules in the illuminated population. And so this point is explained more carefully in the next 2 slides. Okay, so everything that's here is what was already shown to you previously, I guess about 3 slides ago. And so we mentioned it in passing. Now we're going to focus a bit more on what's happening during this decay time period, what's happening in terms of molecular orientation and anisotropy during this decay time, this time period of fluorescent decay. So again, we can look for the moment at a femtosecond excitation experiment. Over some sub-nanosecond time scale, we put in a pulse of light that excites some fraction of the population. Each of those individual molecules then decays according to the kinetic competition between the fluorescence emission process and the non-radiative decay processes. While those decay processes are going on, the molecule is rotating. It's undergoing rotational diffusion, and so that is a probabilistic or stochastic process. It's essentially, not every molecule will rotate exactly in the same way. It's essentially a diffusional process. You will have different molecules rotating differently. But something called the rotational correlation time actually quantifies the net rate of loss of the rotational orientation, or the rotational correlation time captures the net rate of rotational reorientation, and it turns out the net rate of reorientation, the rate of reorientation sort of integrated through an ensemble, is captured by a single exponential, and that exponential is called the rotational correlation time. So now what we can do here to think about that and analyze it, we can look at how the anisotropy would behave after a pulsed nanosecond excitation. After a pulsed nanosecond excitation, again, the fluorescence process will proceed, but it proceeds essentially independently from the rotational reorientation process. The physical properties affecting the different decay rates out of the excited state are not significantly influenced by rotational reorientation. There is somewhat of an exception of that with FRET, but still, in terms of looking at the rotational reorientation of a population, we can ignore even that. So to a first approximation and a good approximation, the rate of rotational reorientation is not influenced by the rate of fluorescent decay. So the fluorescence decay, as we manipulate, let's say, the quenching processes, the fluorescence decay and the fluorescence lifetime will shift around independently from the rotational reorientation rate. Other things might affect rotational reorientation rate, like viscosity, like temperature, like formation of larger macromolecular complexes that rotate more slowly. But the rotational reorientation rate is not affected by the fluorescent process. The rotational reorientation rate can be described by, rotational reorientation as it affects anisotropy. So that is sort of the clever thing about this, particular numerical quantity captured by anisotropy. When we measure anisotropy, that whole Legendre polynomial thing that I sort of skirted over is sort of a clever mathematical approach to getting a quantity that behaves as a single exponential. The anisotropy decays as a single exponential with the time life of that exponential. The time constant for that exponential is the rotational correlation time. The rotational correlation time is a standard measure of the rotational diffusion rate. Again, longer rotational correlation time, longer rotational correlation times means slower diffusion. It takes longer to go down to 1 over E of the memory of the initial orientation. Shorter rotational correlation time, it takes a shorter period of time to go down to 1 over E of the initial orientation. So basically, shorter rotational correlation time, higher rotational reorientation rate, longer rotational correlation time, longer rotational, shorter rotational correlation time, faster rotational diffusion and reorientation. Longer rotational correlation time, slower rotational diffusion and reorientation. So as I talked about in one of the overview screencasts, as things get larger, as temperature gets lower, as viscosity gets higher, rotation rate changes. That will change the rotational correlation time. As the rotation rate, the rotational diffusion rates go slower, the rotational correlation time will go up. As it gets lower, the rotational correlation time, as rotational reorientations gets faster, as it gets slower, rotational correlation time goes up. As rotational reorientation and diffusion gets faster, rotational correlation time goes down. The convenient mathematical properties of the anisotropy are such that anisotropy decays with time instantaneous anisotropy decays with time as a mono-exponential described by the rotational correlation lifetime. Okay, and so so what are the implications? Now, we only need to think about one more thing. Our experiments are generally done under continuous illumination conditions. What anisotropy are we going to observe under continuous illumination conditions, right? With a pulsed femtosecond light pulse, we can just watch the anisotropy decay with time, right? Because effectively here we have the light on at some very brief time window that excites part of the population. We turn the light off, and then we watch the decay in the anisotropy of the fluorescence as the population rotationally reorients itself concomitant with the progression of the fluorescent decay process and other decay processes. So in an experiment using pulse femtosecond excitation, we can just sort of watch the rotational decay or a manifestation of the relation. We can watch the effect of the rotational diffusion or reorientation on the anisotropy. With pulse femtosecond excitation, we can watch that the effect of rotational reorientation very directly. In a continuous wave experiment, we're going to, however, see some steady state output. Effectively, what will happen under those circumstances, we will be looking at the integrated behavior of the population, right? Any individual fluorophore is going to behave probabilistically according to these, the behavior of any individual fluorophore will follow these time-dependent probabilistic decay rates. But the ensemble behavior of the population will be given basically by the integration over time of that decay rate, right? When we look at a given fluorophore, as we talked about before, it will undergo time-dependent there will be a certain time-dependent probability of decay. Those time-dependent probabilities will match the first-order decay rate in the entire population. And so the population will decay according to that first-order rate constant that's shown here. So effectively what we're going to be doing is we're going to be seeing the instantaneous anisotropy weighted by the amount of, right? So at any given time, we will be seeing a given amount of fluorescence given out in the population that was excited, at some starting time. So as the amount of fluorescence, right? So if we start at time 0, we have the maximum amount of fluorescence because we have the most molecules in the excited state. As molecules are lost from the excited state, the fluorescence decays. So we have progressively less and less fluorescence be emitted at subsequent times because there are fewer and fewer fluorophores in the excited state. The instantaneous rate constant for fluorescence emission is the same, but the size of the population is declining, and therefore, as the population declines, even with the same instantaneous emission rate, we see less emission per unit time. The emission at any given moment in time will be characterized in the ensemble by a certain average anisotropy value. Right? And so effectively what we're going to need to do to understand what kind of anisotropy we see at steady state, we're basically going to have to consider, for individual molecules, and individual molecules will behave probabilistically like an ensemble excited at a particular time point. So what we need to figure out now is, right, as the fluorescence in the population decays, the fluorescent emission at any given time point will be the anisotropy in the emission at any given time point will be described by how the anisotropy in the population declines due to rotational reorientation. But what we'll have, to understand what we see at steady state, we'll have to weight, right, the anisotropy at a given time by the amount of fluorescence coming out at that given time. So that's a little complicated, but to restate it, right, when we excite a population, the fluorescence decays as the population in the excited state decays. At any given time, after excitation, there will have been a certain degree of rotational reorientation that will produce a characteristic anisotropy of anything that decays at that time. But at later times, there are fewer things fluorescing because we have a smaller excited state population. So what we're going to have to do is take the ensemble average for the anisotropy at a given time, weighted by the population at that time. So that's described in the next slide.